Okay, the record is now on. So let us finish this. Okay. So it'll be fun. Let's look at this first. Now we have worked on member CD, BC, and up to AB. So now we should be able to say that okay, our free body diagram of every member in the system or in the frame is correct. So we can proceed to write the shear force and bending moment diagram. So now when you look at this, I think we have discussed about this before. So it's up to you to look from the left or look from the right when you want to draw the diagram. But for me, I kind of prefer to look from, as if I was within the frame. So I kind of like to, imagine myself here looking at the frame like this. Just what I prefer. But it doesn't really matter. So for member CD, I will look from the left. Okay, so let me go over the business quickly. I will see this. No, sorry. Okay, and we have the moment. We have the well. Let's try to be nice. Then okay, let's put everything on. CD. The axial force will not change anything. Okay. You know what? Just to here is 8,000, and we have 5,000 and 3,000. Okay, so the shear force diagram, simple enough. It's 8,000 coming down 5, so that's 3,000 and then 0. Right? And the bending moment diagram, we start from, you see, that's the moment. Kind of like the contrast color. That's the moment. And it is like that. So according to your sign convention, that's negative, right? Because your negative moment is like this. So that's negative. So we begin from negative 33,000. So that's your shear force diagram in kilogram force. Okay. And it looks likely because now we have the positive shear area. The positive area in shear force diagram, which should bring this back up to 0, hopefully. And because our free body diagram is correct, so chances are we're going to have the correct diagrams for shear force and bending moment as well. So here is positive area. This area is equal to that's 8,000 multiplied by 3. So that's 24,000. So it should bring this back to just minus 9,000. Correct? And of course, now you can guess that this area should be exactly 9,000. Because right here, I forgot, that's 8,000. And that's 3,000. Okay, so this area is 3,000 multiplied by 3, which is 9,000. So that brings this back to 0. Okay, some of you still think that the bending moment diagram, these two lines are similar or are the same. They are not. Just look at the scale. This is 9,000. This is 33. So I should try to draw it more drastically. Something like that. Okay. Because when you differentiate your bending moment diagram, you will get your shear force diagram, correct? So the values on your shear force diagram are in fact the slope of your bending moment diagram. And when they do not have the same values, that means the slopes should not be the same on bending moment diagram. So they are never the one line if your shear changes. Okay, simple stuff. And you see, this time you will not have the shear force and bending moment diagram similar to the simple beam that you have had anymore, because we are now dealing with different things. So you should stay true to your free body diagram all the time. Right here, your free body diagram says you have the end moment. So you will not have bending moment diagram that begins from zero anymore. You see? And that's your shear force diagram. And whatever you have from free body diagram should give you shear force diagram, and whatever you have from shear force diagram should give you bending moment diagram. You always stay true to that. Don't think that, okay, I used to draw shear force and bending moment diagram for simple beams and it looked like that. Not anymore. Here at C, you don't have the typical pin or roller. You have a rigid joint at C. That's why you have moment. Okay. Now we move on to BC. I'm sorry. For BC, maybe I should for BC now, from your correct free body diagram, you see, now you have, oops, I forgot to put this back on here. Okay. That's your complete free body diagram. Come back here, you now have moment here. Like, you know, let's put the shear back on first, it's easier. 5425, and we have 8,000 here. And here is, of course, 2575, right? You have the axial 8,000, axial 8,000, and then you have the moment 44,400, and then here is 33,000. So you no longer have the member where, you know, the moments on both ends are zero. So when this becomes your free body diagram, you write free body diagram according, you write shear force and bending moment diagram according to your free body diagram. All right. So here we go. Shear force diagram should be simple enough. Oops. On the left side is slightly bigger than the right side, right? According to the load. Kilogram force. That is 5425. So that is minus 2575. You see? Okay, you guys are writing, so you can't. I'll wait. So you see, if you look at your shear force diagram, if it's a simple beam, the shear area here on the left and on the right, they should be equal, right? Let's say if you have a simple beam, if this is P, you know right away it has to be P over 2, right? So that your bending moment diagram will close nicely like that. But here, because you no longer have a simple structure like that, so it's okay for the shear to not to be equal anymore. And in fact, they should not, because you begin with moment not equal to 0. Okay? So right here, that again, this, according to the sign convention, is negative moment. Remember? And that is also negative. You remember your sign convention for negative moment, it's like that. Right? So we don't begin from 0, we begin from minus 44,400. There. Right? And you may as well proceed to, say that here it has to be minus 33,000 as well, coming from here. Oops, sorry. That's a moment. That's a negative moment. And it gives you the value here. So now, what about the value in the middle? You see, some of you, like, I think there are quite a good number of you who just can't seem to draw the bending moment diagram properly. You forgot to, add them up. Okay, so here we begin from here. So the value here must come from the area of shear force diagram here, right? And then again, the area here is 5425 multiplied by 4, right? You must add them up to the existing value, and that gives the final number. So this is not big enough to bring your bending moment diagram to the positive territory. So it only goes up to minus 22,700. Still negative. And then again, this negative area should bring your bending moment diagram down to the value that we already have, which is minus 33,000. So that's your bending moment diagram in the kilogram meter. Okay. Any question? Am I going too quickly? Ooh. Oh, running out of space. Add the page. Oops, sorry. Okay. That's not part of the question, right? Just extend your body, exercising. Okay. So we are left with one member. Okay. So let's get it done. Member AB. Again, I look at AB, I kind of prefer to look at it from the inside. So I'll look from that way. Okay. So that means I will see AB like this. With the uniform load. Like that. And I have the strangely enough, because it's a frame, so you better be careful, because now you will see that your reaction in fact here is coming down. That's why you need to be very, very careful. And then you have the uniform load coming down, and then this reaction will add up and equal to everything. A little bit strange, but it's possible. And then you have the moment, and then the axial force of 5425. When you need to believe in yourself, okay? Because free body diagram is correct. So, are you catching up? Am I going too fast? I just want to spare a lot of minutes for the next frame. I will introduce you to something. So I'm kind of a little bit excited, So let me prepare myself. So now, you see, any question, please? You have any question? No? Okay. So now you can see it's a strange here to begin with. It's downward. So when you see your sign convention for shear force diagram, positive is up on the left, down on the right. So now it's down on the left, which means you begin with a negative value, right? And the total load here, I hate to write like that very much. It's 200 multiplied by 6. So that's 1200, which should bring your shear force diagram down to minus 8,000. See, the negative shear is down and up. So it's up here. So that's negative. So your shear force diagram looks like that. Right? And we move on to bending moment diagram. Straightforward enough. This is the slope. So your bending moment diagram will like that. Oops. Simple stuff. So you should see that insofar, this word, I speak a lot. I think it fits the content. That's a word, insofar. Means up to now. Okay. So insofar, we haven't done anything new in terms of the equilibrium and free body diagram, except pushing your boundary a little bit further by showing you that when you dealing with members in the system, that in this case it's a frame, you can face the free body diagram that is not something that you're used to when you're dealing with a simple beam. Now you have end moments, okay? And when you thrust your equilibrium. When you know that your free body diagram has end moments, they must show on your bending moment diagram, correct? So I find it depressing a little bit and disappointing that many students would be able to complete the free body diagram, but they get absolutely confused when they want to turn the free body diagram into the bending moment diagram, because they don't trust what they have. They will go back to what they're used to when they're dealing with the simple beam. This is no longer a simple beam. Okay, it's a system. It's members in the system, and in the system, we join the member together by a rigid joint. The rigid joint is something that is capable of transferring moment from one member to another. So when you have the moment at the end of your members, your bending moment diagram must show exactly the same thing. That's the point. Okay. So here we are. We move on to something new. That is the part where you can have something like this. You see that? This load is neither perpendicular nor parallel to the member. So this will push your basic understanding, knowledge about the free body diagram to the limit. Because when you see this, I ask you this. I always ask students this. Can you define the beam? What is the beam? What is the column? So it's only typical that students will answer, a column is a vertical member and beam is a horizontal member, right? No, because let's say if this is your column, you think it's a vertical member, right? But if I put the load there, is that a column or is that a beam? Is it a column or is it a beam? It is a beam, right? And you think that's a column? If I put the load there, is that a column or is that a beam? It's a column. So what is the definition of the beam and the column then? It has something to do with the direction of the load, right? The column is the member that has the load parallel to its principal axis. On the other hand, the beam is the member that has the load perpendicular to its principal axis. So when you have the load perpendicular, do I spell correctly? The load that is perpendicular to your member will produce bending moment and shear force. So you have been writing your bending moment diagram and shear force diagram with the load that is perpendicular to your member all along up until this point, right? It's basic stuff. Am I right? You always do that. So what if I'm not a mean person? This is what really is in the real world. This is what you have to deal with. If I have a beam and then the load comes in like that, what do we do? Are you going to change yourself into the Ultraman or something like that? I'm going to change. I'm the Power Ranger, that sort of thing. So that means if you face a situation like this, there will be the component of the load that will produce bending moment and shear. And yet there will be a component that will produce the axial force as well. And do we use or do we write the bending moment based on the axial force? Can the axial force produce bending moment? No. So that means when you're faced with a situation like this, you need to account for the vertical component only by using your beloved trigonometry. Correct? If you do not realize that only the vertical component or the component that is perpendicular to your member that produces a shear and moment, you are including the axial force into your shear force and bending moment, which is wrong. So we are pushing the boundary a little further. Yeah, just like when you are comfortable. No, we're not done yet. We just need to keep moving forward. Right? So when you face a situation like this, you know that you cannot use the uniform load like this to calculate bending moment or shear force anymore, because they are not perpendicular to your member. And do you think I make this up? Just look at your roof, man. When you have the roof is like that. Right? The ventilator. Oops. Like this, right? And life load too. It's real. It's there. It exists. And we go back to the beginning of the class when we talk about the fact that you need to know what load there will be on your structure. So we're not doing anything away from what we've been talking about at all. We're just making your life a little bit more miserable, that's all. By giving you the truth. If you have seen the movie The Goodfellas, when Jack Nicholson screams at the Tom Cruise, you can't handle the truth. But you have to, right? Because you want to be engineers. It's not really well gone. So I don't think I can do much about it. So let's say, how many examples I talk about? Okay, look at that. Nice, huh? Real structure. So let's say it could be part of the tunnel, right? And then you have the weight of the soil above the tunnel coming down. It's real. I'm trying to, whenever I create something, I always think about what can actually happen in the real world. So this can be your tunnel, it's strange shaped tunnel. And the tunnel has to support the weight of the earth above it. It's real. Something that you need to deal with. So I think I'm not going to push it anymore, okay? But except let's try and see how far we can go, because we have 5 minutes. At least we try to finish the reaction, so next time it can be quicker, okay? All right. Or yeah, at least we can name it. So let's call it A. B, of course. C, D, and E. Yeah. And again, you should know, if you fail to calculate the reactions, you're not going anywhere, right? So without further ado, you know that if you have only one, notice that even though this uniform load, right, it's not perpendicular to your member, but it's a vertical load, so it doesn't give anything in x direction, right? So you can still obtain your sigma of x equal to 0 and solve for reaction at E very easily. So that's 6 tons. And then you can take moment at A, sigma m A equal to 0. Or you want to take sigma ME first too, but you already know that this is 6 tons, right? So which one you want to do first? Sigma MA or sigma ME? That doesn't matter. Okay. Let's say sigma MA equal to 0. So now we have 3 ton meter per meter multiplied by 6. That's a total load. And you have the resultant coming in here. So that's multiplied by 3. And this is giving you clockwise moment around A, just like the horizontal load as well. So that's plus 6 multiplied by, oh, be careful. It's pretty tricky here. The distance is 10, not 7.5. Okay, minus the reaction here, 6. This distance is, that's 7.5. So this is 2.5, right? And then say minus RE multiplied by 10 equal to 0. Okay. So RE is 9.9 tons. Okay. So that's 9.9. And you should take sigma m equal to 0. Then you have right here, I should begin with RA, it's easy, more easy. RA multiplied by 10 minus the uniform load, which is 3 multiplied by 6. But this time, when you take moment at E, the distance becomes 4 plus 3, right? 6.5 plus 4. So that's 7. Okay? And then my plus, but minus because they are now in the same direction, plus 6 multiplied by 7.5 equal to 0. So RA is 8.1 tons. Looks nice. 8.1 plus 9.9, that's 18 in total. And we have the uniform load resultant is equal to 18. So looks like we have the correct reaction. Okay? I just want to, arrive at the member BC a little bit if possible, so that next time we can begin at BC right away. Okay, so let's just a few more minutes. Okay, sorry about that. So the reaction should be easy enough, but you look at member AB again. That is, sorry, that is the a lean column, right? No load on member AB, and it's a roller support. So AB is straightforward enough. That's why I'm pushing a little bit. So for member AB, it's like this. You have reaction 8.1. So that is also 8.1. Then that's it. Why 8.1? Really? So for member AB, it's nothing. It's there, just I don't know why. Maybe it's part of the structure that has to look like that. But when you come down to member BC, that's where the problem begins. Because coming in from AB, you also have this 8.1. But this time, the load is like that. And as I say, we can't use this load to draw shear force and bending moment diagram. So we need to find a way to break this load into two components. The component that is parallel to the member and the one that is perpendicular to the member. And we will use the one that is perpendicular to the member to draw our shear force and bending moment diagram. And we'll do that next time. Okay. Any question? You know what? I'm still recording it. Regarding the mistake that John made, I make in the grading exam, I will try my best not to deduct the points that you guys already have, but I will try to find a way to add to the ones you've done correctly. Okay, I think that's fair enough. Maybe. Okay, but I think I'll try to make extra notes. Okay, this is not right, but you know, then again, I'll try to do that. Okay, because if you think about it, you forget the load, and then that beam is not correct. So I'll try to do that, but see, it's my mistake, yes, but I will do what's best for you. You need to know what's right, and I'm afraid that I'll try not to deduct points, but if I don't, you will remember it incorrectly. That's what I'm afraid of. It may sound a little bit unjust to you, but what is right and what is right, what is wrong is wrong. The most important thing is to learn the correct thing, so that you make sure that you don't make mistakes like this when you do the work. And I think that's the most important thing. And maybe yeah, like I really couldn't believe it. It was just 2 bad weeks that I've had. Well, I didn't know that it would affect me. Apparently it did. Anyway, for those of you who will come, I think let me stop the record first.